Welcome to Lecture 12. We're going to be studying arm motion planning. The key goal for arm motion planning is to find a high-dimensional trajectory that goes from a desired start point to a desired end point. This can be done both in joint space or task space, also known as Cartesian space. Other constraints or goals that we must meet while we generate this trajectory is to avoid collisions. The arm should not hit itself, nor should it hit the environment. This trajectory will also be subject to optimizations and constraints. Some constraint examples are the trajectory should never force the arm to reach a joint limit. It should also never be forced to saturate the actuators. So the torque generated by the motor should not reach the limit by that motor. The trajectory should be optimized to be smooth. When we have smooth trajectories, motors work more efficiently and tend to not hit saturation points as much. Sometimes you might want to optimize mechanical advantage if the robot has some advantage. If a specific endpoint endpoints and a trajectory are required, you might have to constrain the velocity. All of this should be working optimally online or real time, such that the robot motion is useful in real life experiments. And if latency is not a problem, you can use a supervisor to first plan a trajectory, and if desirable, then continue to execute it. Now we start section 13.1, where we study the problem of Cartesian motion planning. In this section, we study the planning approach, and then in the next section, we look into the details of how dynamic programming is going to be used to optimize, select a sequence of optimized motions for smooth trajectories. Then in section 13.3, we study how to integrate all of this code into ROS to actually make it run on a robot. Here, we assume that we're always interested in following some 6 degree of freedom path. It could be Cartesian or joint space, as we talked about before. Sometimes we may desire to have a fixed orientation along the path, such as a robot carrying a cup. Other times we may not have this stringent constraint. And so let us move then to 13.1 and thinking about the planning approach. The way we start this is first by saying, let's approximate the path by a number of waypoints. Once we have each of those waypoints, we want to compute the inverse kinematics solutions for those points. And if we have more than one solution, we want to find the best sequence of solutions. For all of these purposes, we're going to mainly focus on the Cartesian planner package. This package has examples for 3 robots. 7 degree of freedom arm robot that we see here on the left. Then we have the UR10 Cartesian planner code, and finally the Baxter Cartesian planner code. So for all of these robots, again, the way we start is by sampling points. We have a path that we want to approximate. We select points with a particular degree of coarseness or granularity. That means how high the sampling rate is going to be. If the sampling is not too high, maybe we're not going to approximate that trajectory very well. When we compute the inverse kinematic solutions for each of those points, we may have more than one solution. That is represented by Q1 to Qn. Why might we have more than one solution? One reason might be simply coming from the mechanical design of the robot arm, where Cartesian goal points might have elbow up, elbow down, right arm, left arm types of solutions. But another reason is that if we're using a redundant robot, where the controllable degrees of freedom of the robot are greater than the total degree of freedoms in the environment, we can have more than one solution. So any robot that has 7 degrees of freedom more and that is trying to compute solutions for a 6 degree of freedom space has that additional degree of freedom. What that means is we're going to have a lot of possibilities, maybe infinite number of possibilities to solve our Cartesian pose. So imagine the robot is carrying a cup and so your wrist or your tool is either pointing up or pointing down. So that the two orientation axes are set. The way you hold the cup will fix, say, the y-axis of rotation and might also fix the x-axis of rotation. But there's one axis that is free to rotate in any direction. That'd be the z-axis of rotation with respect to the tool. And that is the yaw angle. And so that yaw angle can actually, could be 0, could be 45, could be 30, could be 15, and you're still going to be holding that cup in the right direction. So you might get many inverse kinematic solutions from there. Finally, you have the joint space planner, and here's where we use dynamic programming to actually select the best sequence of solutions to have our smooth motion. So here we're going to be assigning cost to different solutions, find the minimal cost, and then generate the sequence of motions. For the algorithm, we're going to have a start configuration, a final configuration. Normally, we're going to feed in to the joint planner a joint configuration, and then we're going to output a joint configuration. These can be changed from Cartesian pose to joint angles and vice versa. Once we have the start and end point selected, we need to then select the kind of generated trajectory that we want. Here I'll introduce 2 examples for you, but in the code we have a total of 9 different command modes or techniques. The first one is, let's say you want to generate a joint space trajectory. So the start and end points are both joint angles, and we don't care exactly how the arm moves in between. So here the arm doesn't move in a straight line. There's some curving between the points, and we also don't control the orientation of the tool. So this is one possibility in terms of generating a plan. We could also have a Cartesian space trajectory where we provide an end effector pose at the beginning and the end, and then we want to find, we might follow a straight line trajectory from between those 2 points. In terms of the orientation of the tool, the orientation might reach the final tool orientation quickly in the trajectory around this point, and then just continue holding that orientation throughout the motion of the robot. We could also have it where the orientation of the tool is fixed the entire time. Okay? If you want to see all the possibilities that we have encoded, you can click on this link, which takes you to slide 26 and shows you our action server message. And here in the goal section, we have a variable for the command code, and here you could see the list of different codes that we can use for different motions. Our Cartesian planner package will also need support then from 2 other packages, kinematic solvers and joint space planners. For example, if we're using the 7 degree of freedom arm, we can find the main code for the Cartesian planner here under the source file. For the kinematic solver, we change to this package, arm7.dov fkik, and in the source file we can find this code. And then for the joint space planner, we can go to this package and in the source folder find this file. At the end of our planning, what we're going to do right now for section 13.1 and 2 is simply write a file of poses. So this file will contain the optimal sequence of joint angle poses that the arm would visit given a starting and an end point. Well, let's look at an example. Let's look at some code example. Imagine that we want to move the robot with the flange pointing up through a path. This would exemplify the robot carrying a cup, and maybe the sampling rate that we wish to follow is sample at every 0.1 radians and have and then based on the trajectory we're going to hard code in this file, we might have 60 waypoints. So here we can do raw set Cartesian planner example arm 7 degree of freedom Cartesian path planner main.cpp. So here at the top you can see that we have a fixed z desired, a fixed y desired, and then a range of motions for x from negative 1.5 to 1.5. You see here the file that we're going to write towards the end. We're using eigenvectors here, so we set the flange start and end points. and this is where we can see the way in which we instantiate an object of the Cartesian trajectory planner class. If you look into the particular class, you'll see that we get some main functionality like getting the pose of the gripper, and then calling some planning trajectories that really facilitate just the design of the code in terms of doing the planning. So once we set the pose, orientation, and translation for the start point and for the finishing point, we can call the Cartesian path planner method on this class and provide the start point, the end point, and what this is going to return is this optimal path variable that has an array of optimized joint angle sequences for our motion. And then basically we can just write these to file and then get the motion going. Okay, so that is summarized here as the key part. And then if we want to run this, we just do ROS run with a ROS core ahead of that. So sorry. So here we might say, let's see, did I have it here? ROS run Cartesian planner example arm 7 degree of freedom Cartesian path planner main. Now notice that we don't have a robot running. This is just doing showing you an example of how this might look in terms of planning on a hard-coded trajectory. Let me summarize this for you in the presentation, but this is just the way it runs. And here it's finding the optimal sequence starting from the last waypoint, 60, all the way down to the end. And it's going to show you the optimized sequence of trajectory points here. So the way it works is something like this. Number one, compute the total number of IK solutions at each point. So we're testing the null space for different yaw values. So we might be at step 8, for example. And then we're looking at different yaw solutions, yaw at 2.7 radians, 2.8 radians, 2.9 radians. And in some places you may not find an IK solution, but in other places you will. And just in this 8th waypoint, you might have 272 inverse kinematic solutions. Okay, then because we have so many solutions at each waypoint, we need to find a way to compute the best one. We're going to use dynamic programming. That's important because, as you see, let's say you have 100 waypoints, you have 272 solutions or so for each one. The number of solutions explodes. So we need a very effective technique in doing the computation of optimization. So here we're starting with the last layer and moving towards the front and analyzing the costs for all of those solutions. Finally, we find the optimal path by computing a trip cost that we're going to look in our next section, and and then just return those solution points. So if you look at the file output, it might look like this, and each line represents the arm configuration. So we have 1, 2, 3, 4, 5, 6, 7 joint angles for our 7 degree of freedom arm, and each configuration is the best IK solution for the Cartesian pose set point at that waypoint. And all of these together is our optimized joint space selection. So you could use this in two ways. You could use this offline if you just read the trajectory from the file and publish it to ROS. You could move your robot offline. But if you want for this to work online, then we need to actually get this code into action servers to do the planning and the execution on demand.